Welcome back, everyone, to another explainer. Today, we are following the script structure outlined in our source document titled ENGV to dive into a frankly bizarre historical anomaly. On paper, June 17th is just your standard, run-of-the-mill midsummer day. But in the realm of mathematics, it is this wild focal point of sheer coincidence and world-altering breakthroughs. We're going to explore how four massive mathematical leaps, all tied to this exact single date across different centuries, quite literally built the physical and digital infrastructure we rely on every single day.
Across completely different eras and countries, brilliant minds on this specific date tackled some of the most massive spatial and computational puzzles imaginable.
So, have you ever actually thought about the routing algorithms in your phone's GPS? I mean, we just expect a tiny handheld device to instantly calculate the absolute fastest path through millions of possible intersections in a sprawling city grid, right? But to pull that off, it needs a flawless mathematical model of the physical Earth.
And that foundational model actually traces back to June 17, 1714, the birthday of a French geodesist named César-François Cassini. He essentially walked right into a massive scientific showdown. Isaac Newton theorized the Earth was flattened at the poles, while rival scientists swore it was elongated. To settle the score once and for all, Cassini used a genius method called triangulation. Instead of trying to measure vast distances by physically walking them, he laid down this giant invisible network of geometric triangles stretching across the French landscape. The beauty of this is that if you know the exact length of just one side of a triangle and the measurements of two of its angles, you can mathematically solve the entire rest of the shape. By chaining these massive triangles all the way from Paris to St. Malo and Strasbourg, Cassini created the very first highly accurate, mathematically sound maps of an entire country.
He effectively took the lumpy, completely irregular shape of the Earth and turned it into pure, solvable geometry. And it's exactly because of his foundational geographic coordinate system that modern satellites can pinpoint precisely where you're standing right now. All right, moving along our June 17th timeline, let's make a bit of a conceptual leap from measuring physical borders to inventing the math needed to create entirely new ones. Welcome to the Netherlands, 1898.
Think about the incredible textures in your favorite video games. How do those engines render endless, perfectly repeating graphics on a flat, two-dimensional screen without crashing the system's memory limit? It is a colossal mathematical hurdle.
Which brings us to Moritz Escher, born, you guessed it, on June 17, 1898. Now, ironically, Escher actually admitted he was pretty terrible at school arithmetic and struggled with his exams. But everything changed after he visited the Alhambra Palace in Spain and became totally mesmerized by the geometric Moorish tiles. He dove headfirst into these incredibly dense crystallographic papers, stuff he barely even understood at first, and unknowingly mastered what mathematicians call the 17-plane symmetry groups. He learned how to manipulate geometric planes using translations, rotations, and glide reflections. This basically meant he could take incredibly complex shapes, like intricate drawings of birds or lizards, and shift, spin, or mirror them so they lock together perfectly. He figured out how to mathematically divide a flat plane so those shapes could repeat infinitely in all directions without a single microscopic gap. Escher proved that you don't just crunch abstract numbers. You can actually apply strict geometric rules to trick the eye and capture infinity right on a flat canvas. Every procedurally generated endless pattern in our digital world today fundamentally runs on those exact same symmetry groups.
Still on this exact same date, we jump forward just a few decades to England, moving from rendering infinite graphics to organizing infinite data. Before we had the raw computing power to just brute force our way through sorting data, we desperately needed a logical architecture. Without it, complex databases would just collapse into total chaos. So how do your apps process massive arrays of data instantly without a single glitch? You need an absolutely impeccable underlying structure. That structured logic leads us straight to Frank Yates, a pioneering statistician who passed away on June 17, 1994. Yates realized that to solve messy, multivariable real-world problems like optimizing crop yields to secure food supplies during World War II, you had to extract precise data without all the different variables cross-contaminating each other. To pull this off, he heavily utilized complex experimental designs, specifically 6x6 Latin squares. Think of it kind of like a Sudoku puzzle. It's a grid where every symbol appears exactly once in each row and exactly once in each column. By applying the strict mathematical structure to field experiments, Yates was able to perfectly isolate multiple variables at the exact same time. And his concept of flawlessly structured arrays translated perfectly into computer science. In fact, when early computers hit the scene in the 1950s, Yates enthusiastically bought one for his lab and pushed everyone to start writing logical, machine-independent code to sort these massive arrays.
In an era when a lot of pure mathematicians still turn their noses up at mere machine calculation, Yates fiercely argued that to be a good theoretical statistician, you literally had to compute. He knew that mathematics and algorithmic computing needed to merge, laying the direct foundation for the data arrays our software runs on today. Map geometry, infinite graphics, data structures, let's make one final jump on this timeline to see how this state even tames the sky above us.
Modern aerospace engineering relies heavily on fluid dynamics. Have you ever wondered how engineers calculate the forces acting on an aircraft? It requires tracking billions of independent gas variables. The air isn't just some static object, it's a wildly unpredictable, dynamic system of continuous collisions.
Providing the mathematical clarity for that invisible chaos traces right back to June 17, 1939, with the birth of Italian mathematician Carlo Cercignani. This guy was brilliant and largely self-taught, learning complex calculus straight out of encyclopedias as a teenager. Cercignani dedicated 45 years of his life, even while battling severe health issues like MS, to mastering the Boltzmann equation and the kinetic theory of gases. The big problem he tackled was bridging the gap between macroscopic randomness, literally billions of molecules bouncing around chaotically, and macroscopic predictability, which is the smooth, continuous flow of air you absolutely need to understand to design a working airplane wing. He formulated exact mathematical models that accurately described how microscopic chaos scales up into measurable fluid dynamics.
Cercignani mathematically proved that irreversible, predictable macroscopic laws actually emerge perfectly from reversible microscopic chaos. He essentially took the most unpredictable physical system and locked it into rigorous equations so that modern airplanes can fly safely and efficiently.
As we pull all these threads together, the true significance of these historical milestones becomes crystal clear. Every single person we've explored today, spanning centuries and borders, all incredibly tethered to June 17th, was ultimately tackling the exact same concept.
They all faced a messy, totally unpredictable reality and asked, what is the pattern hiding inside the chaos? By daring to seek out those strict geometric and algorithmic rules, they laid the groundwork for GPS mapping, infinite digital rendering, instant data sorting, and global flight. They proved beyond a shadow of a doubt that beneath the apparent randomness of our universe, there is a beautiful mathematical structure just waiting to be mapped. So as you look around at the highly structured technology driving your everyday life, what pattern will you discover next?